Hello everyone. Today I want to talk to you about two rather short but very important topics. And one of them is something called Kirchhoff's current law, or KCL, and the other one is resistors in parallel. Those are very much related because you can only apply KCL when you do have some kind of parallel configuration. So first let's talk about KCL. So KCL has to do with current, like the name clearly states. So let's take a look at the currents in this particular circuit that I have over here. So first my current comes out of the battery, and then it keeps on going up until it hits this point. Let's call this one I total. So my current. Now once it hits this point, and we call this junction, it starts splitting up. Some of it will go over here. And some of it will go over here. Now, please keep in mind that current is something that you cannot use up. So your current is always constant, your total current. So that means that once they split up, at this point where they merge together, we're going to get back exactly the same current we had before they split up. So at this point, I once again have the total current coming back into the battery. So a few takeaway points over here. First one, that the current is conserved. We're not using up the current. It's not that you can have a situation where you can have one current coming out of the battery and the different current coming back into the battery. No, no, no. If that is happening, you have a part of the circuit that you don't know about, where the current is leaking somewhere. So in the proper circuit, the current is most certainly conserved. Or it is far more accurate to actually say that it's charge that's conserved. Charge cannot be created, it cannot be destroyed, it's conserved. So I'm gonna put that one. Or more accurately, charge is conserved. Conserved. I'm not sure that's how you spell this word. Yeah, that's right. Okay. Okay, there we go. All right. So charge cannot be created, it cannot be destroyed. Well, we know that because if we try to destroy an electron, we need an outright nuclear reaction to do that. The other takeaway we can take from this picture is that our currents, when they split up, they still have to add up to the current that they were before they split up. So let me put that down mathematically. This is going to be my I1, and this one's going to be my I2. And this is really the KCL. And the KCL stands that the sum of the currents in the circuit has to be equal to the current coming out of the battery. So the current coming out of the battery is I total. And of course, it's equal to I1 plus I 2. And that is really all that KCL says. Right? Just like KVL, just like Kirchhoff's voltage law, KCL is very, very simple. Okay? So the charge cannot be destroyed. Whatever comes out of the battery has to come into the battery. And the sum of the current equals the current coming out of the battery. So I'm going to spell it out. Now this is actually a bit of a baby version of the KCL. A proper version would be that the sum of the current coming into the node or junction equals to the sum of the currents coming out of the node. So I want you to be aware of that definition. We're not going to so much use it, but it's pretty obvious too, right? Whatever comes in here has to come out. That's all it says. All right. So the second topic for today that I want to talk about is resistors in parallel. Okay, so I'm gonna add a nice picture, and it's gonna be exactly the same picture that you guys saw above. Okay, so once again we have two branches, and in each of those branches you have a resistor. Now what I want you to think about it is a supermarket and the checkout at the supermarket. Imagine that you have just one checkout. All you can do is just go through one checkout, and this resistor is going to be your checkout. Eventually, if you have a lot of customers, it's going to create a lot of resistance because there will be a long line, right? A line is basically an indicator that there is a lot of resistance, right? People can't go through fast. So what does a manager do? A manager goes ahead and opens up another checkout line. Now we have two of them. And all of a sudden, people get their purchases faster. So what I'm getting at, remember how we were talking about total resistance? If I'm going to have an equivalent circuit, here's my equivalent circuit. Here's my battery. And this is also 2 volts. And this is going to be my R total. It just so happens in this case that it is quite obvious that when you open the second checkout in the supermarket, you don't slow down the speed with which people get their purchases. You actually speed it up. So in this particular case, we know that R total is actually less than the sum. Well, that should make a lot of sense. If we have them in series, then they slow things down. But if we have 2 parallel checkout lines, like in a supermarket, we speed things up. And if we speed things up, we decrease the resistance, right? Remember how we were saying that current and resistors resistance are inversely proportional to each other. As resistance goes down, the current goes up. Well, this is exactly the case. This is exactly the case. So what is the actual formula for R total over here? The actual formula for R total over here is actually somewhat unpleasant. And the reason for that is that it's not going to give us R total proper. So it's going to be 1 over R total equals 1 over R1 plus 1 over R2. So this is the formula for the resistors in parallel. That's a bit of an unwieldy formula because once you solve for 1 over R total, you actually have to solve for R total itself. But it's a useful formula and it's a correct formula. And ultimately, it's not that bad. I will show you eventually how I got that formula and where it's coming from in one of the supplemental videos. I will be putting up some supplemental videos. Those are not required to pass this course. You don't have to know where this formula comes from. But if you want to, I will definitely make a video. Alright, so this is all I wanted to say over here.